All right. Thank you so much for being here, everyone. I am super excited to deliver my PhD thesis, my defense. My thesis is focused on developing computational tools in order to make it easier for people to design and fabricate their own custom robots, targeting researchers, industrial designers, and hobbyists. And to motivate why I think this is so important, I want to first turn to nature. Nature is diverse and it's highly capable. There are a number of different organisms that have evolved over the years. Each is capable in a number of tasks, but none is a master of all tasks. Each is a master of its own trade, and this has been evolved over many, many years. If you look at the top, you see the cheetah, which is the world's fastest land mammal, the gecko, which is the fastest climber, the tardigrade on the bottom right, which is gosh darn near indestructible. On the bottom left, you see the sailfish, which is the fastest underwater swimmer. And on the left, you see the sand flea, which can jump the highest, most body heights compared to its own size. And part of the reason why nature is so capable is because the organisms are so complex. If you look at an organism, it has a number of different organ systems that are working together in harmony. Organisms have dense sensing and neuron-powered skins. They have bones which encode topology and tissue which also encodes materiality for things like compliance and elasticity. Muscles have been strewn throughout the bodies through evolution and optimized for organisms being able to solve certain tasks. And this is all wrapped together in a central planning and cognition system. Meanwhile, by contrast, this was the state of the art in robotics 6 years ago. And this was actually a huge win. I'm showing the failure really here, but this was the DARPA Robotics Challenge where robots were able to solve a number of tasks. But here, if you look at all the different failures, you also see how much further there is to go. Robots fail on a lot of more simple tasks. And if you watch this was a competition for humanoid robot designs, and you'll see that many different teams had their own robot design, but they all feel a little bit suboptimal here, right? There's no richness of the organ systems that you see in biology. They're a little bit rigid, they're a little bit clunky, they move funny, they have little integrated sensing. And part of that is because of the way in which they were designed. These robots are really, really expensive. And once the body is built, the teams had to do the best that they could with the robot's morphology, hell or high water. I should also stress that these bodies weren't necessarily designed specifically for the tasks that they were meant to solve. They had to solve a number of tasks, and people were doing this mostly from a biomimetic standpoint. I'd like to take this moment to make one more point. This on the bottom right here, this is Atlas. This is one of the robots that was used in the challenge. On the left, you see 10 years ago, and on the right, you see today. And if you've seen the videos from Boston Dynamics, you know just how far their humanoid robots have come in the last 10 years. But from another perspective, you can say it took 10 years to build something that still struggles to do everyday tasks, such as construction, cooking, etc. And if design cycles are this slow, how many more decades is it going to take to get a diverse future of robotics? So why did teams struggle so much in the DARPA Robotics Challenge when the robots failed? Well, as I hinted before, current workflows for robot design are extremely slow. And that's particularly because people are working on spiraling linear workflows. And what I mean by that is that first a designer develops a conceptual design of how they want the robot to move. And based on that, they select the actuators they want to use for a task. Then they design the body to house those actuators and define concretely how the robot will move. And then they program it with control or higher level AI reasoning. And if they realize then that the robot is not performing as desired, they may need to revisit as early as actuator selection and repeat the process. This is slow, hardware intensive, and suboptimal. As a bit of a corollary of this, because mistakes are so expensive, designers tend to play it safe, and they stick to what works. Here's a handful of quadrupedal robots that have come out over the last few years, and it really does feel like every other month, somebody is releasing a new quadrupedal robot. And while this is cool, this isn't quite the diverse future of robotics that I was hoping to sign up for. The dream of a robot-filled future is one that takes inspiration from nature, where a robot fills every niche. The mantra should be that robotics abhors a vacuum. And while we see some different morphologies that get some attention, some more than others, particularly humanoids and robot arms, most of these task-driven robots are actually research or concept grade, and others still are reserved to science fiction. If we want capable robots, we need to make it easier to explore algorithmically and interactively. Now, I'm not the only person who's been working on robot design. There's been tons of work where people have looked at the body and the brain of the robot for both rigid and for soft robots. My research, though, is specifically focused on developing a workflow where all aspects of a robot are co-designed and co-optimized at once to build a sophisticated robot that can solve specified tasks, such as robustly traversing uneven terrain. The thesis is this. Algorithmic tools can be used to vastly accelerate the design and fabrication process of rigid and soft robots in a single CAD/CAM workflow by jointly reasoning about all aspects of robot design in a single physically predictive pipeline. Here's the view from 40,000 feet. For the purposes of this defense and the fact that I only have about an hour to talk to you all, I'm focusing on 4 main contributions of this talk. Each will add a new layer of complexity to the co-design tale, although each also brings its own unique contribution. We'll start by talking about how do we co-optimize robot shape, then materials and proprioceptive models very briefly, and then we'll end by talking about how do we optimize robot sensors. But in every single one of these contributions, we're not just going to be optimizing over these one domains, but we're actually going to be adding other domains to the mix. So co-optimizing over things like control and motion and actuator selection. These contributions have been solidified in 4 main papers that I'm going to talk about, and most of this work will be simulation-based, but with an emphasis on being physically accurate so that the robots designed by these algorithms may be fabricated in the hopefully near future. But I'll touch upon some fabrication results throughout this talk. So without further ado, let's get started. And I'd like to start by actually going a little bit deeper into why co-optimization algorithms are necessary to begin with. I want you to look at this, this cartoon hexapod. Imagine that this hexapod, which is 10 centimeters off the ground, has to walk and hit a button that is 15 centimeters off the ground without jumping. This is not drawn to scale, obviously, but if you don't want the robot to jump, then what the designer is going to have to do is they're going to have to redesign the robot. They're going to have to make it taller. But something happened when we made the robot taller. We've changed the dynamics of the robot. We've changed the forces that are going to be applied and the torques that are going to be applied due to the motors and by gravity. And not only did we change the dynamics of the system, but we also changed the kinematics as well. So the robot went from having a short stride to a much longer stride. And as you change the dynamics of the system, it means that necessarily you're going to have to revisit the control. If you change the control, you might need bigger or smaller actuators. If you change that, you might need a bigger body to house the actuators in. And this all leads back to our spiraling workflow. So let's talk about our options when it comes to robot design. First, one of our options would be manual workflows. These are what we talked about before. They're slow, spiraling, expensive. We're not going to be about that in this talk. Another option that we could have is alternating optimization. So this is very similar then to the manual workflow of that spiraling and expensive. But rather than manually going and designing each aspect of the robot and going back and then and revisiting each aspect, we're going to computationally optimize each aspect. So we'll optimize control, and then we'll optimize the body shape, and then the actuators, and then we'll go back to control. This sounds like a pretty promising direction to go, but sometimes it leads to problems. It can lead to poor local suboptima, since only certain bodies are compatible with certain controllers. So this is a little bit better, but I think we can do still even better. And the way that we're going to focus on in this talk is full co-optimization, where we solve for the best body, controller, and actuator simultaneously in a single optimization workflow. But there's a slight issue here, there's a challenge, and that's that it's hard enough to solve motion, and now we're saying we want to solve for motion, control, and actuators. Our solution is going to be rooted in something called trajectory optimization, so I'm going to briefly review that now. Trajectory optimization works as follows. Given a starting pose of a robot and a target pose that you want it to reach, and maybe some constraints such as maximum actuation limits, trajectory optimization is a procedure that finds the actuation input for every time step such that when simulated, the robot reaches the goal. Now this is feasibility. This is, can we find a path that reaches the goal, such as this cart pole swing up, but sometimes you want to do a little bit better because there's lots of different trajectories which can solve a task. So you can also optimize over things like maximum power consumption of a motor, average power consumption, or maybe you just want to solve for feasibility. We can actually solve these problems more efficiently by converting them to the direct transcription form. I'm not going to focus on all the details here, but just note that we can solve even for things with contact. But the key to solving these types of problems is that we need to compute the gradients of all the constraints of the system, which means that we need to be able to compute gradients of the dynamics with respect to all of the decision variables. We need to be able to determine the gradients of the dynamics with respect to all, gradients of the contact constraints with all variables, and also, we need to be able to reason about state and actuation. Algorithms for solving this are pretty well understood at this point for control. What we proposed in this paper and our core contribution was this realization that you can also add design variables into the trajectory optimization framework, when we call this procedure parametric trajectory optimization. This is possible because the dynamics and all the constraints of these problems are smooth and continuous in the space of design parameters, which makes that co-optimization solvable with gradient-based methods. And people often ask me here, is this even true for contacts? Can you have smooth contact constraints with respect to design parameters? What happens if you make the legs longer and they would suddenly tunnel through terrain? But we can parameterize the contact constraints as well, and solve for optimal forms even for problems with contact. So let's summarize nuts and bolts how we actually make this possible. Nonlinear optimization requires gradients of nonlinear constraints with respect to all decision variables. That can be computed efficiently. Lots of people have worked out the equations for this. And it's actually implemented in a toolbox called, not that Drake, this Drake. It's implemented in Drake for everything but the design parameters. And so this is a lot of work to try to write the gradients of a robot's dynamics with respect to every design parameter. And the reason why that's so difficult is because there's so many different types of parameterizations you could have for a robot, and you want to parameterize it over geometric parameters. Maybe you want to use something fancy like cages. Maybe you want to use inertial tensors, optimize over inertial tensors. So instead of writing this out explicitly, we symbolically differentiate the dynamics in order to generate C kernels for performance boosts. I think this was actually the first example of symbolically differentiating some rigid robots through all these constraints. At least I had to implement this from scratch because I couldn't find anything available. So this is a pretty simple idea that we're going to co-optimize over design and control, but it can lead to some pretty powerful results. So as inputs to this problem, you take in a fixed topology that is parameterized. So all the link extents, all the inertial tensors, all the densities of the system, that's all parameterized. And then you specify, like I said, tasks and objectives for your motion planning task. In this example, we want the front of the hexapod to hit the button, which is off the ground. It's too short, so it's going to have to change its design parameters. And then we also have two objective functions which we add together. We try to minimize the maximum actuation. This is particularly nice because it allows us to choose the smallest actuators necessary. And we also regularize this with respect to design parameters to keep it as close as possible to the designer's vision. As outputs to the system, you get an optimized robot morphology, an optimized robot controller, and it also selects the actuators via the objective function. So let's get to the fun results. In this example here, we're going to have a rigid biped that's going to try to hit a button that's too tall for it again. In all the examples you're going to see here, the robot was actually unable to solve the problem in the default configuration. We always made the robot too short, or we made the robot too heavy, or usually both. Here you'll see a task where the robot clears the step, and actually there's only one configuration of the links that works here. The top links have to be shorter so that the robot can lift its leg and not collide with the step. Here's an example where we did a quadruped, and we'll actually optimize this over two objectives. First, energy efficiency, so we can choose the smallest actuators necessary. And in the second example that you're going to see here, this is just the same video twice. And the second example you're going to see here, just to show that we optimize it for a quickly moving gate. And finally, in probably the most challenging example here, this is called either the scorpion or the squirrel, depending on what you see. We have two constraints. So we want the tail to hit a certain point, and we want the front of the body to hit a certain point. And we actually put joint limits on the tail so that it can only bend a certain amount. I think it was like 60 degrees or something. There's actually only one configuration of the link lengths that can actually solve this task. So that was pretty exciting that it's able to find that. Now we are able to fabricate these robots. So here is an example of us fabricating the hexapod. It matches pretty well modulo friction. Friction modeling is actually something that's very difficult in SimSurreal right now. So, and if you're the evil empire, you might want to optimize your AT-ATs to crush the rebel scum. One of the cool things here is that the AT-AT, as it's going up the ramp, it wants to stand up. So the solver actually optimized to find the longer legs in the back and the shorter legs in the front so that it can still stand upright while it's on the ramp. In conclusion, we're able to co-optimize over the skeleton, going back to our idea of optimizing these optimal organisms. We've shown that we're able to optimize over the parameters of a skeleton, control, and actuators here. And design optimization can transform what are normally specified as infeasible problems into feasible ones. And this is made efficient through gradient-based methods. And here we specifically use symbolic differentiation. But nature isn't fully rigid, and compliance and elasticity are important features animals use to solve these tasks. Which brings us to our second contribution, where we focus on materials and soft robotics, which have much richer dynamics and have much more degrees of freedom than rigid robots, both for control and for design. Specifically, in order to solve this, we're going to present a fast, accurate, and differentiable simulator, which we call Chain Queen, which is meant for soft robotics. And I want you to pay attention to that third word there, differentiable. What do I mean by differentiable simulation? Simulation looks like this. A soft robot is inherently an infinite dimensional creature. If you take any soft object, a piece of elasticity, you can see that any point could theoretically be stretched in any direction. So any point in the body can deform in an infinite number of ways. Thus, rather than try to reason about this entire beast, we use what's called an observer function, where we feed a reduced state of the robot, a short summary into a controller. Now, for the purposes of what you're going to see here, the observer that we use is just clusters of the soft robot, and we average their positions and their velocities. And we feed that in as a summary. So that can be fed into a closed loop controller, which generates an actuation signal based on the state, which can then be used in a forward simulation step. And after stepping the system forward for the length of the simulation, we summarize the robot's behavior with a loss function, which we seek to optimize. Example loss functions could be something like energy usage, which you saw previously. But for soft robots, we're actually going to do this in an unconstrained fashion. And I can talk offline if you want to know why we choose unconstrained optimizers here. So our objective is usually going to be something like how far forward does the robot walk? After we simulate forward, we perform what's called a backpropagation step, where we compute the gradients of the loss function by applying the chain rule recursively and back to the start of simulation. And then we feed those gradients into any first or second order optimizer. Now, part of what makes a simulation differentiable is that any variable of the system can be differentiated with respect to any other variable. Differentiable simulation is a bit more powerful than the symbolic gradients that I talked about earlier. Since differentiable simulation can have a more complex program structure, it can have things like if statements and for loops and such like that. Now, you may be wondering why I suddenly started talking about simulation. Well, it's because the differentiability of simulation is so important in solving soft robot co-optimization tasks. And also, we're going to be using this simulator for the remainder of the talk. Now, I said that the simulator was differentiable, accurate, and fast. So why do you care? First of all, when you have differentiability, you have gradients. Like I said, you can use continuous optimization. And that really allows for some exciting applications in control, system identification, and design optimization. Second, if it's accurate, it gives us promise that we can actually fabricate these robots in the future. And third, simulation is always the inner loop of any design algorithm. For each iteration of an optimization algorithm, you're always going to want to simulate your robot to see its performance and compute gradients in order to know how to update the system. So the faster you make the simulation and the gradient computation, the faster that you actually make your optimization algorithm. Another thing people ask me is, why do we actually care about using differentiability for control? I've heard about this cool thing called reinforcement learning. Everybody's using it these days. Reinforcement learning is really powerful, especially for rigid robots. But we've actually shown that if you use model-based differentiable simulation and use the gradients from that, it's possible that you can actually improve the robot up to 10 times faster than you would for control than reinforcement learning. And even for situations where there's contact, it becomes even trickier. I'm yet to see that much research really showing that it's feasible to use reinforcement learning on walking soft robots. Lastly, there were plenty of existing simulators, but the key thing is that we occupy a unique space where we have full differentiability and we're doing soft robotics. So this was actually a necessary step. So the simulation itself is rooted in something called the material point method, or MPM. It's a very expressive simulation method. It can handle things like snow physics. So this was used in the movie Frozen. by Disney. It can handle fluids and elastic coupling. It can even handle things like fracture, which is a feature or a bug, depending on how you think about it. And it's physically based, which makes it really perfect for soft robotics. MPM is a hybrid particle grid simulation method. So particles are the main representation of the geometry, but for each time step, they're rasterized to a grid and advected. While on the grid, elastic forces are applied between neighboring grid cells, momentum is updated, contacts and collisions are resolved, and then the system is resampled in its particle form and is graded forward in time. Most of the time throughout this talk, you only have to think about this as a collection of particles, as if these are the atoms that are making up an elastic body, but occasionally we'll talk about the grids. Now, MPM by itself isn't new, but what we've done here is we've added the ability to compute gradients of any output of a simulation step with respect to any input, and we put it on the GPU to make it very efficient. And obviously, the idea of differentiability isn't completely new. For people in the audience who are familiar with deep learning, right? Differentiability is what powers these learning systems today. And if you are familiar with deep learning, you can think of a single step of simulation as you would a single layer of a neural network. In this sense, a differentiable simulation is really just a really nonlinear deep neural network. Okay, now let's get to the demonstrations. As a first motivating example, we're going to show how gradients can be used to infer physical quantities. So here, ball A will collide into ball B, and we want ball B to land at destination C. This is going to be, where the ball lands is going to be a consequence of momentum and conservation of momentum. So we define a loss function, which is how far does the ball end from the observed destination? And then we compute the gradients with respect to the relative density. And over time, the system learns that the optimal density, relative density in order to get the ball to land there is 2.26. That's a simple example, but maybe more interesting than this is something like control. We can use the gradients of the objective with respect to the control parameters to directly optimize the controllers. And in this example, we're going to be using pneumatic actuators, where the red actuators are ones that are currently contracting and the green ones are ones that are currently expanding. So first we'll optimize this 2D biped runner. It has 4 actuators, and the goal is to move to the right as quickly as possible. And what you'll see here is that over 58 iterations, the robot learns to walk forward just by using vanilla gradient descent on the computed gradients. This is a pretty exciting result because this system is pretty complex. Each has thousands of degrees of, the system has thousands of degrees of freedom. And we can do this very quickly. Each simulation and gradient computation here can be done in less than a second. So we can optimize this entire motion in less than a minute. And we can actually do better than 58 iterations at this point. This was using vanilla gradient descent, but if you use something like Atom, which is a little bit fancier, a little bit smarter, then you can do this in 10 to 20 iterations. So really fast control optimization. Maybe a little bit more realistic is 3D. So here's that quadruped you saw earlier, 4 actuators in each leg. And you'll see that it's able to optimize its control by vanilla gradient descent. We don't have to just do walking. We can also do a soft robotic arm where we make the objective the distance to this blue sphere. This is a multitask example. So the controller is general, that's learned is general. You just say where you want the sphere to be, and no matter where you put it, the robot will optimize to hit the sphere. And a lot of people ask me, are you stuck with blocky geometry? Can you do things other than blocky geometry? And the answer is yes. So for the Pokemon fans in the room, here's Bulbasaur. It's going to learn Tackle Attack in 100 iterations or less. So you can just input a mesh into the system as we've designed it. It'll add the particles automatically. All you have to specify is where are the actuators, and the robot will learn to hop forward. Okay. So that's enough for control, but now what we're really excited about in this talk is co-optimization. So the question is, can we co-optimize soft robots? One of the most powerful aspects of differentiable simulation is that anything can be differentiated with respect to anything else in the simulator. We can differentiate with respect to closed loop control parameters, open loop control parameters, or really excitingly, the material properties of every single particle in the system. That's the Young's modulus, or the stiffness, the Poisson's ratio, or the compressibility, and the density of every single particle in the system. And this can create soft robots with spatially varying materials, which hopefully someday can be realized by something like voxel-based 3D printing or metamaterials. That's potentially thousands of controller parameters and potentially hundreds of thousands of material parameters. So we're going to start by motivating this with a soft arm example. This soft arm has four actuators, and similar to the rigid problem, we've made this arm too stiff in order to get the red ball to the green ball in its default configuration. This arm is going to have to learn two things. One, an actuation sequence where it oscillates back and forth so it can build up enough momentum to hit the green circle, and also a material distribution that actually allows it to hit this with optimal efficiency. So to demonstrate, here's the results that we got out of our optimization procedure, and you'll see something really nice emerges here. The red sphere gets pretty close to the green sphere at the end of this, much closer than it's in the default configurations where it's unable to move back and forth really at all. And the really nice thing here is that we see that the soft material aligns itself on the outer spine of the arm here. And that's the part that's going to stretch the most. So that's the part that needs to be the softest. So this is a really intuitive and exciting result. We can also do this for walking robots. These are examples optimized using the Atom optimizer. I'm just going to show you a biped and a quadruped here. But as you watch this, you're going to see that the material distributions, they optimize over all the different parameters, and they optimize in a way in order to allow the robot to walk forward with a harmonic oscillatory pattern that's extra efficient. And you'll start to see like a little skeleton will start to emerge over the different optimization iterations. So you can see that more compressibility occurs in the middle where it needs to deform more. And it's also made a little bit stiffer there so that it has structure. Now, I want you to, one thing you're probably asking yourself here is, or asking me maybe, is what's the point? Does this help? Why would I do this? And the answer to that is a resounding yes. So optimization actually improves with every new variable, every new design domain that we add to this, right? If you look at the blue curve at the top left corner there, that's what happens when we optimize this robot purely control. And for each colored band that you see above that, we're adding a new variable to the design framework. We're adding the Young's modulus or stiffness. We're adding Poisson's ratio. We're adding density. And at the very top, that gray band, that's what happens when we co-optimize over every single domain at once. So really adding more co-optimization domains can give up to a 40–50% improvement or 20% in the case of the octopod. But in all these cases, it's giving a monotonically increasing improvement, and it's a non-trivial improvement as well. So I'm really excited and hoping that people start to look to co-optimization because it can really improve their robot designs. So in summary, fast simulation allows for fast gradient computation. Fast gradients allow for efficient optimization. And efficient optimization allows for some cool applications. And here, going back to our organ system example, this is where we optimize the materiality, the soft part, the rigid part of the robot, and if we want to build our ideal complex robot organism. If you want to play around with this code, it's available online. So let's summarize the story so far that we know. Co-optimization can help design new robots that can solve problems that were previously infeasible with the default design. Co-optimization can also lead to designs that perform better than the default or naive solutions. And finally, co-optimizing over more domains can lead to better results and scale to really high dimensional problems. But what happens when we hit problems with more complex or combinatorial structure? And our solution to that is going to be learning-based approaches. This is going to bring us to our third result here, where we're going to co-optimize over control materials and proprioceptive models. I'll talk about this one pretty briefly before I move on to some other results. So if you recall, this is how we defined a robot simulation. Now, last time I showed you this picture, I didn't go into the detail about the observer function. I mentioned that closed loop controllers really need reduced latent spaces in order to work efficiently. But in the chain queen work, we just sort of clustered groups of particles and extracted features from them. This has two problems. First, that's kind of an ad hoc process that can require human tweaking, and it's not really physically measurable. As a solution, we presented a method for simultaneously learning an observer function with a descriptive latent space at the same time that we co-optimize our robots over control and or spatially varying materials. You can imagine, in order to do this, we're going to imagine an external camera model, basically, that's going to look at the robot as it moves. This transforms this manual workflow into one that is automatic and learned. Now, the secret sauce to making this happen is that NPM also occurs on a grid, not just a particle representation. And previously, I haven't talked too much about that grid, but it actually stores momentum and velocity information on how the robot is moving. So you can sort of imagine these images. These grids are like images where the red channel stores how much the robot is moving in X, and the blue channel stores how much the robot is moving in Y. We don't really need a green channel for this. The nice thing about it being grid and image-like is that it's the perfect data structure to be interpreted by deep convolutional neural networks. And further, these deep learning architectures are completely differentiable as well. So we can backprop through simulation, which includes backpropagating through the controllers and the learned observer function. The algorithm we use to optimize this has two alternating phases. And it's one of those alternating optimization algorithms I mentioned previously, and I'll explain why in a minute. In the first phase, the observer is fixed, and we use the gradients from a differentiable simulator in order to optimize the controller, just as we did before. But one of the core insights of this paper is that this procedure actually wastes a lot of information. We're using the gradients, and we're throwing out everything else about the simulation, the trajectory of the robot, the path, how it got there. And our realization is that you can actually store the frames of the simulation in memory, in a replay buffer, and use this in a learning phase, which we interleave with the optimization. It's a way to add much greater data efficiency in an optimization algorithm. In this learning phase, we use the saved frames to learn an encoder via a variational autoencoder framework, which serves as an observer for a very descriptive latent space. Now, some considerations here. Why did we have to use an alternating optimization framework? Well, we couldn't simply co-learn the encoder during the backpropagation phase, is what we found. The encoder learns too slowly, and the controller tends to get stuck in poor local minima as a result. We also had to store some extra grid frames in a replay buffer to improve the training stability. And we also use target networks, which is a trick from another paper called Deep Deterministic Policy Gradients, and a few other papers. This improves training stability. And the learned representations actually lead to much better controller convergence and much better design convergence than if you don't use the learned observer. And that's because the observer function isn't this ad hoc clustering method, but it's actually something that is catered to the observed dynamics, the dynamics that emerge over control optimization and also design optimization. And the latent representations are actually pretty meaningful. So these are saliency maps of the subspaces of the robots. And on the left-hand side, you can see it's mostly white noise at the beginning when it's starting to learn. But over time, it converges to learning these really meaningful subspaces of how the robot is going to move. Okay, but what if we wanted to actually deploy these robots in the real world? I said this worked based on an external camera model that's extracting the robot's velocity. This isn't something we're really going to be able to do in the real world. So what if we wanted to control and understand these robots using embedded strain sensors instead of an offboard camera? Can we learn the sensor structure? And that's going to lead us to the final part of this talk, which is co-learning sensors and tasks for soft robotics. Now, like I said, if we want to control these soft robots in the real world, instrumenting the whole world with extrinsic sensors, such as cameras or mocap devices, is pretty impractical for obvious reasons. But luckily, in recent years, we've seen incredible breakthroughs in strain sensing from soft robotics. But embedding such of these sensors into robots can be complex. It can be time intensive. It can be expensive. But now the decision of where to put these robots is also a manual, human-driven process. But something that I'm going to show you guys a little bit later is that humans are actually quite bad at sensor placement. In this project, we presented a method for simultaneously solving two deeply coupled problems. The first problem: how do we solve soft robotic tasks purely from strain sensor information? For example, here you see a gripper manipulating an unknown shape, and from a time series of just the measured strain and strain rates experienced throughout the gripper, the problem in this example is to determine the shape of the object being grasped. Now, of course, we can't measure the strains everywhere on the gripper, only at sensor locations, which we have to strategically place. So the second problem that we co-solve then becomes, given a budget for a maximum number of sensors we want to place on the gripper, Where do we place them in order to get the most bang for our buck? What sensor placements lead to the best performance of the task at hand? Our solution is going to be to take a novel machine learning approach to this problem, and from data simultaneously learn a model for solving a given task while co-designing for intrinsic sensor placement. We'll use a new deep learning architecture that can be used in about both aspects of this project simultaneously. And what separates our method from other work is its generality. We're going to show you results on 3 to 4 tasks, depending on how you count, and 7 different robot morphologies, 4 in 2D and 3 in 3D. The secret sauce is our deep learning architecture, the point sparsifier and feature extractor, which can be composed with other off-the-shelf machine learning models to solve all sorts of problems. So for example, we can combine the PSFE with 2 other well-understood machine learning models, an LSTM and a predictor layer, to solve supervised time series learning tasks, such as determining the stiffness or shape of a grasped object. A second application is state reconstruction for soft robots. From just the measured strains and strain rates, we are able to determine the robot's state in the world, that's its deformation and its deformation rate. And I want to stress that this works in both 2D and in 3D. Finally, we demonstrate that representations learned for pose reconstruction can also be used for closed-loop terrestrial soft robot control. I should stress that we actually only tried these 3 applications because they were the ones we were most interested in. So really, there could be all sorts of tasks that our model could help solve, and we just haven't tried it yet. Let's discuss our assumptions here. The only physical aspect we're designing is the sensor locations, and believe me, that's hard enough. Actuation is fixed, and sensor locations will be chosen from a very large number of dense possible candidate locations. I haven't drawn all of them here, but there are over 400 candidate locations in our examples. Secondly, each sensor measures 4 pieces of information in 2D, or 6 pieces of information in 3D. That's the strains and the strain rates on the Cartesian axes and in material space. And by material space, I mean that as the soft robot deforms, the measured directions deform with it as you would physically expect. In this work, we're working purely in simulation, but we've made deliberate steps to design our method such that it could be applied to real physical systems, right? We're using the physically based elastic simulation that we talked about earlier. We measure strains in material space. We've made sure our method is robust to noise and so on. The vision is that you would design your model in simulation and you would deploy on corresponding real world hardware. The 2 main assumptions we make are that we have no sensing latency and that sensors are small enough to fit on nodes in simulation. We choose the material point method, or MPM, as a simulation method, but that's just an engineering choice. So the method is applicable to any node-based method, such as FEM, SPH. It's not simulation dependent. All these would work. Finally, I won't talk about it too much here, but we performed a suite of experiments where we injected 1% sensor noise, which is more than you would find on off-the-shelf strain sensors. And our method works almost as well as with no noise. So this is a real data sheet of a real strain sensor. It has 0.65% accuracy error. So we are accurate to robust to real world tolerances. Okay, so I've talked up the PSFE architecture. So what is it? I think there are 2 big ideas in this paper. So here's the first. Most simulation methods treat soft robots as collections of nodes. Because of this, we make the realization that, much like how we used the grid before, you can think of each time step in a soft body simulation as being a point cloud. And that's great because the machine learning community has not only created grid-based learning methods, but also architectures for reasoning about point clouds, such as the point net architecture. These methods, which our technique is inspired by, efficiently treat the input point cloud as an unordered point set. But there's a bit of a problem here, right? If our robot is a point cloud, what are the coordinates of each node? We can't measure the XYZ coordinates of each node. We don't have extrinsic sensors, only intrinsic sensors. So the natural thing here for each node to measure is the strain and the strain rates of each node, because that's what we can measure. The problem is that these aren't really spatial dimensions. So this just gives us a histogram of the strains and the strain rates throughout the body. So for the gripper example, if you were to flex it vertically, or if you were to shuffle all the particles around, these would have the same histogram and they would be treated the same. So as an additional input for each node, we also provide the rest pose, the material space coordinates, which allows us to use these great point cloud representations while still disambiguating between strain distributions that have the same histogram. So in total, this is 6-dimensional coordinates for each 2D node and 9-dimensional coordinates for each 3D node that we're going to feed it. Unfortunately, feeding in all the simulated strains and strain rates would require sensorizing the entire robot, and as we said, this is not feasible. So here's the second big idea, and I think this is a pretty cool one. Our architecture itself is also what figures out where to place the nodes. The input layer of our model is special stochastic neurons, and they drop out the unimportant inputs over time, learning which are the important inputs for solving a task. Physical design hereby becomes the dual of this learning process. By learning if we do or do not need a certain node's information, we learn if we actually do or do not need a sensor at that location. So here's a quick cartoon. At the beginning, we start with all nodes having an equal probability of being used or not used. And over time, the distribution of probabilities over all nodes will go to 0 or 1, giving us a sparse collection of sensor placements. The number of sensors is controlled by a sparsifying or regularizing loss function, which we can add to any other task loss, and pushes the number of sensors towards a user-specified sensor budget. The full algorithm is as follows. First, offline, we generate an entire data set of several simulations in different scenarios and record the strains, strain rates, and rest geometry of the robot, and any prediction labels. Then iteratively, we do the following 3 tasks. We first use the data to compute how good our model performs on such task losses as how accurately it can predict the shape from a collection of different shapes. Then we compute the gradients of the model parameters with respect to task loss using a backpropagation scheme. We have to take care here to compute the gradients because they're stochastic, so we have to compute gradients that work in expectation. And finally, we use these gradients to perform stochastic gradient descent, and we do 2 rounds of training, one where we treat the nodes as stochastic, and then when they get close to converging, we clamp them to 0, 1 in a fine-tuning step. All right, now for the fun results here. In this example, the gripper must disambiguate between a circle, a diamond, a triangle, and no shape. So that's no object being placed there. And we build the data set by sampling these shapes in many different sizes and positions and add actuator noise in order to make the problem harder. So the model must learn to disambiguate the quality of the motion and can't memorize motion sequences. This is the confusion matrix of the trained model on our test data set. As you can see, we're able to get over 95% accuracy with just 5 learned sensor placements. Strikingly, we compared to a baseline where we placed sensors in random locations, and it was unable to solve this task at all. Training actually fails, showing that sensor placement and code training is important. By the way, in the paper, you can find comparisons to the random baselines for all tasks, and our method wins throughout the board. Here's a visualization of the learned sensor locations, and you'll see they make semantic sense. They tend to appear near the inside of the gripper, which is what's interacting with the environment the most, and they barely appear on the stem. PowerPoint tends to fail me exactly on this slide, and I have to restart it. Yep, okay. 1 second. I don't know why this happens, but I think that the future of HCI might be making PowerPoint that works. This is a very open problem, as you can see. Okay, I hope that this is still, everybody can see this. Okay. Nice. Okay. So back to this. Here are some demonstrations of state reconstruction. First, some of the examples that we get the simulated data from. And then you'll see the reconstructions in normalized coordinates. So colors represent deformation rates in X, Y in blue. X is green, Y is blue here. And the closer the colors match, the closer the deformation rate. So you can see we have really good correspondence here, both in deformation and in deformation rate. Here's a 3D example on a soft hexapod. Again, the data first. And then here's the robot from several different orthographic views, side, top, and front. And again, we have very good agreement in deformations and deformation rates. And here's a really interesting and exciting result I hinted at earlier. Not only are we across the board better than random sensor placement, but we're better than human placements, and significantly better, as much as 60% better. In fact, we did a user study, and the results were that humans are even worse than random in most cases. And that's actually because humans are tricked and pick antagonistically bad sensor locations a lot of the times. For example, on the robot, on the elephant robot, Humans chose to put sensors at the feet because they thought that these were geometrically important features, but the feet don't actually deform much. If you want to get good performance, you need to put the sensors on the trunk. And as a final demo, we trained our model for state reconstruction and then used the model as input to a multi-layer perceptron controller for a control task and trained the controller. This needed more sensors to be consistent and reliable. I think we used 15 or 20 here, but I think this is the first demonstration of closed-loop terrestrial soft robot locomotion, even from sparse intrinsic strain inputs, even in simulation. So this is all being controlled from strain inputs. Now, people ask me, can we actually fabricate these things at some point in the future? So looking forward, I'm really excited about fabricating these optimized sensor layouts, and I'm especially bullish on textiles as a sensing medium for soft robotics. Here you can see a quick demo of a textile-based glove that can reconstruct wearers posed with state-of-the-art accuracy. And you can imagine a bunch of maybe cool AR or VR applications here. And this is powered by a novel fluidic sensing and resistive sensing architecture that reason about forces and strains. And it's interpreted by a downstream neural network, much like in our simulated case. And right now we've placed these sensors down manually, but I'm really interested in automating their placement. And there's all sorts of stimuli that this sort of sensing architecture can actually sense. So you can imagine some really interesting applications. And this is sort of moving us towards optimizing these soft robotic organisms with optimized robot skin, going back to our organ metaphor. So to summarize, I'm really hoping that computational robot design is going to be a force multiplier for the field, right? Transforming these spiraling workflows that iterate between the different domains into one that is not just the computer taking over, but rather the human working with the computer in order to design the robot. The computer maybe explores different designs, it optimizes, it plays around in its own imagination, and it sends some ideas back to the human. And the human then looks at these results. The human then, based on that, can refine what they want, their conceptual design, their constraints that they want to put on this, the objectives that they want the computer to optimize, and sends it back to the computer. And this sort of becomes a dance back and forth. This was all tied together. The first project that I worked on during my PhD defense or thesis was this composition-based program called Interactive Robogami. And while it only works on kinematics, it captures a lot of this in its form, right? And you see it's able to resize the different aspects of the robot to match user intent. It allows users to explore different control sequences and play around with different types of motions, and interactively gives them previews of how the robot's going to move. And what you'll also see here is that it also allows users to play around with what the different parameters of the system will be, and it guides them in the optimization. So it's interactive. You'll see there's little arrows here that appear that tell the user how do you change the parameters of the system for optimal performance. And if you want, you can have the computer take over. You can hit a button and it'll optimize for like how fast the robot can walk forward, or you can do it in this interactive fashion. And this whole workflow is tied together by not only this CAD procedure, but also a computer automated machining procedure where we export the designs to a 3D printer. They can be fabricated and they match what humans are able to, what humans see in the previews. These are the types of workflows where you need to be moving towards, and I'm hoping that the types of optimization algorithms that I showed today could be integrated into workflows like these. As far as impact, I'm hoping that this work will really speed up the depth of the designs, right? Speed up the design process, maybe make it 10 times faster for engineers to design robots, and also the breadth of the different designs here, right? We want new novel morphologies and behaviors that we maybe wouldn't have explored as humans. We want computers to help us in this exploration process. Okay, so for the last 50 minutes or so, I've been talking to you guys about my thoughts on the future of robot design, and that's actually what I've been doing for the last 7 years of my life. I'd like to take a few minutes to get up on a soapbox and talk to you about what I think the future of robot design is going to be. We had this big idea at the beginning of this talk that we wanted to do full co-design. We wanted to optimize for sensible skins. We wanted to optimize for sensor placement. We wanted to optimize for bones, materiality, actuator placement, and central cognition. And we've optimized over each of these domains along with some brain components, some controller. But what we really want to do in the future is optimize for all these simultaneously in one grandmaster algorithm, including things which I didn't have time to talk today such as tendon-driven actuator designs, which match muscles, right? We want to be able to optimize over all these different organ systems at once, and hopefully, we can build robots that can actually approach the harmony that we see in nature. Another thing that I think is going to be really important in the future is going to be sim to real for any robot. Now, if you're not familiar with the term sim to real, it's this crazy notion that the things that work in simulation should actually work in the real world. And even though that should be obvious, it's actually a really hard problem. And so in recent years, there's been a lot of success, but it's very computationally expensive, and each of these actually only works on a single robot design. People spend many hours trying to solve the sim to real gap for a single robot. And what I'm really excited about and I think is really important in the future is if you want to design a new robot and you want to hit print, and you want it to be 3D printed, you want it to ideally walk right off the printer in the way that it was designed to. And so how do we actually make sure that our workflows are going to be predictive for all these crazy novel robots that are going to come out in the future? I talked a lot about how valuable differentiability was in a lot of these problems. And I talked about mostly for soft robots and for rigid robot domains. Differentiable simulators are becoming really popular in a whole bunch of different domains right now. Each time they mostly work in a single domain. So not only do we want rich multi-physics engines, like something like CompSol, but we want to be able to compute the gradients with respect to any design parameter in one unified workflow that can capture all the phenomena of rigid, soft, hybrid robots. And finally, I think that this is extremely important, that we need to start thinking about tools for users and not just for researchers. I spent a very long time making all these research grade algorithms, and I think a lot of other people in the field have as well. But I'm sort of yet to see these algorithms be put in any real software. And I think in order to really know how useful they are, we need to put them in front of users, get users using these algorithms and seeing what the impact can really be, and make sure that they're catered to users in terms of usability and not just for researchers, right? If we really want this field to thrive, it needs to become useful to somebody in the near future. All right, that is the end of the technical portion of this talk. I'd like to end by saying a few thank yous to some people that made this defense possible. So first and foremost, I'd like to thank my wonderful and inspiring and supportive and patient advisors. I'd like to thank Daniela Roos, who believed in me and gave me an opportunity, first as a research engineer in her group, and then as a PhD student, and then allowing me to contribute to the Printable Programmable Machines project, which evolved into this work for my PhD thesis. And I really thank you for teaching me how to perform research, how to communicate my results, how to, always encouraging me to keep the gradients. I know everybody says that, but it's really important. And thank you for pushing me to think big and bold, but also reasonably, and always push for impressive results. And I felt under your guidance, every project had the opportunity to be great. Second, I'd like to thank Wojtek Matusek, whose creativity and ambitiousness really inspired me every day. It really challenged me to think about how to make good research happen, taught me how to be thorough, how to formulate research problems, even translate those into successful grant proposals. He really immersed me in several enriching teaching experiences. And most of all, he taught me that with some clever thinking and some hard work, what looks like it's impossible can actually be made real. I'd also like to thank Pulkit Agrawal, who's the third member of my thesis committee, who consistently offered some advice during the finalization of this thesis. I'd also like to say thank you to some of the closest people during my life during the last few years. I'd like to thank my parents, both who were incredibly supportive. My mother actually got sick on the very first day of my PhD and sadly passed away. I would have loved for her to be here to see this work completed. I'd like to thank my caring and supportive partner, Gloria, who was very patient during all my late nights working on papers and was always there, especially for some tough times in the later end of my PhD. I'd also like to thank a special thank you to my Daniel Jackson, who's my academic advisor, who really cared about his advisees. I always felt if I needed something that I could turn to him, and he was an incredibly welcoming and kind person. I think she may have just left, but I'd also like to thank Mika, who basically just makes the lab run, and I don't know how she does it on a day-to-day basis when she runs like 3 labs, administrative assistant duties. I don't know how she does that. I'd also like to thank Britt, who is Wojtek's first administrative assistant, who I can only describe as utterly irreplaceable. And I'd also like to thank Roger, who took over at Brit and filled some very big shoes. I'd also like to thank 4 people who served as early mentors for me. The 4 of these people really showed me how to navigate all the complexity of academia and showed me the ropes, both for the forest and the tree views of how to formulate and tackle complex research problems on a broad and a day-to-day scale, and how to think about publishing and conferences, and really brought joy into my early PhD life. Also, I'd like to thank 3 internship mentors who gave me some cool experiences outside of MIT over the years. I'd like to thank 5 friends outside of MIT who gave me some really incredible and invaluable career advice, both at the transitory periods of at the beginning and the end of my PhD. I'd like to thank some of my closest collaborators over the last few years during my PhD, and all of their incredibly insightful and amazing work in making these contributions happen. And then finally, I'd like to thank all the other collaborators who I didn't realize how many I had until I put them all on the page, and it's really humbling, including UROPS and MNGs. And I'd like to thank all of my lab mates. I hope I got everybody here. I'm sorry if I missed anyone, but you've become more than just coworkers over the years. You've become friends and family. And really last, I'd like to thank my cat, who's really cute and was actually my most consistent roommate during my PhD defense process. So with that, I'd like to thank you so much for your time, and I will take any questions.
Thank you, Andy, for the talk.
Yeah.
So the thesis committee includes myself, Professor Wojciech Matuszczyk, and Professor Pulkit Agrawal. And we're gonna do the next phase of the defense in 2 steps. First, we're gonna take questions from the broad audience, and then we're going to have a closed session with Andy and the committee. And so, are there any questions? Let's see. Let me first see whether there are any questions from those of you who are in the room.
Yes.
I was just wondering, for the first and second part of your presentation, landscape resulting optimization problem, did you feel like there were lots of documents? Did it always work, or did you have to do
That's a great question. For the rigid robotics work, we had to see several initial guesses. I would actually say that the algorithm succeeds about 40% of the time on most of those problems, which maybe sounds a little low, but it's not really that big of a deal. You just run it a few times and eventually you get something that works. A lot of times it gets stuck in infeasibilities. For the soft robots, there's really no constraint there. There's no way of saying that it really failed. Optimization can't fail. You just get sort of bad results sometimes. That doesn't happen very often for the examples I showed. These really converged very consistently. We did try other morphologies that struggled a lot more. As you make the dynamics of the system more complex, the system is more prone to getting stuck in local minima. So as an example, there was one time I was really excited. I was going to make this soft, fully lanky biped that was all like soft legs and everything like that, and it just kept falling forward. It's really tricky to actually come up with what's called the sort of in reinforcement learning, it's known as the reward function. But here it's the objective function. If you make it something greedy and you just apply something like gradient descent, the robot's first instinct is, and maybe you saw it in one of these videos, the instinct is to just fall forward. I'm going to push my head, which is what I'm trying to optimize. I'm just going to make it fall forward. So there's a lot of emergent behavior that's unfortunate that's in there. So I think this is some really interesting future work of how do we make this not get stuck in local minima by adding exploration rather than these gradient-based methods. Yep.
Andy, can you actually stop the slideshow, put the rest of the book up, and let's see if there are questions from the online audience?
Yes.
What I just said.
Hi, everyone. I don't know if you heard what Daniela just said, but we're taking any questions from the Zoom audience. So if you are, if you have a question, I think just raise your hand. I'll go back and forth, and I will call people. I see some people put questions in the chat actually, or I see one question in the chat. So I'll take this question first. Leo asked, there are some design parameters that are inherently discrete. For example, the number of links or particles in a system. how can we deal with parameters like this in gradient-based optimization without making the optimization landscape excessively complex? That's a great question. I think you saw that gradient-based methods are sort of limited in handling discrete or these combinatorial problems. There was something I didn't show where there are certain problems where you can do certain tricks and change the problem into like into a sparsification problem. We did that for the cable work that I didn't quite show. But you'll see that, we did solve for some discrete structure, the sensor placement, using learning-based techniques. So we did that with the sensor placement example. So I think learning techniques are actually really, really promising for solving for complex discrete structure. There's some other great work that I was fortunate enough to help out on, that's not part of this thesis, on automatically solving for topologies. I think that if you want this, you're going to have to mix some sort of learning-based method, something with search, with a learning-based method. So you'll have to combine learning and search in an intelligent way. You won't be able to just completely do continuous optimization. But that's a very good question. If there are more questions, I will. You can either put them in the chat or you can just raise your hand using the emoji or whatever it's called on the Zoom. But if there are no questions, then I am, okay, wait, there's one question. Are changes in physical properties considered with temperature? No, we didn't really look at temperature at all in this work. That would fall into why I think multi-physics is so important, right? We simulated over dynamics of elastic bodies, for instance, but we never really looked at how different types of temperatures would affect material parameters. I think it's really easy to add, or maybe not easy, but it's relatively straightforward probably to make a continuous material model that can be where you can do something like domain optimization, randomization, and optimize over different material temperature values. But this is something that we didn't consider.
I have a question, actually.
Yeah.
At the risk of asking a similar question to the first one, do you see fundamental limitations for like adding additional actuated degrees of freedom, especially like if you're looking at humans? A lot of the redundancy is the important part, but finding how to design that redundancy seems hard. It seems like with trajectory optimization based methods, as you get to many degrees of freedom in terms of the actuation, is that like as you're like adding and subtracting those, is that still tractable?
So the question here, if I'm understanding this correctly, is how can you not tractably also optimize for solving for the number of actuators that you'd put on a robot?
And placement.
And placement, yeah. This is something that we didn't consider in most of this work. There was a project that I didn't show that where we do this. I think that this is actually a really exciting area that I'm currently trying to look into. I think we can probably use some techniques that are similar to the sensor placement work in a reinforcement learning framework to try to learn where do we put the actuators. There's one more question in the chat which says, when assessing a human's ability for sensor placement and saying that is worse than random, who was asked to place the sensors? It was a bunch of engineers who had, that's a good question. It was a bunch of engineers who had knowledge of continuum physics. So these are people who should be privy to the nuances of these materials.
Okay, so with this, let's thank Andy for his presentation once again.